All right, it's my pleasure to welcome all of you to the John Postel Distinguished Lecture Series. We have a very exciting speaker. First, he has a cool title, has the Yahoo Chair Professorship. Has been a distinguished faculty member at Stanford University for a number of years. And along that, he also created this company called Rambus. Many of you are familiar with as a company that provides the very high performance IPs between memories, processors, and high-speed peripherals. Since then, his group has done a very exciting pioneer work along the line of energy efficient computing, which is also dear to the heart of many of us here in this room, in the audience. So with that, I have the distinct pleasure to welcome Professor Mark Horowitz to be our distinguished speaker.
Thanks, Jason. Okay, so today what I'm going to be talking about is computing's energy problem and what we can do about it. As you might tell from my intro, I'm actually old. I've been in the IC business for over 30 years now. And during that period of time, I've been basically working on building digital integrated circuits. And recently, we've really come to notice that we're facing this big challenge moving computing forward. So to understand why this is an important problem that we should all care about, everything that we have today basically has a computer inside of it. And in fact, if you go around thinking about how many computers you own, the numbers are far greater than you would ever imagine, because your computer that you think about actually has a very large number of computers in it. There's a computer in the keyboard, there's a computer in the display device, so you have tons of computers. Your devices at home have computers in it. This was brought home relatively forcefully for me when my refrigerator, it's not this model, but it started acting really funny. So I called up the service place. And they said, oh, it's probably the microcontrollers got into a weird state. You should just reboot your computer, right? And so I had to unplug the refrigerator to reboot it. When you're rebooting your refrigerator, you know something's a little weird. But my favorite example of the fact that computing is incredibly cheap is the fact that we send computers to each other. So computing is so cheap, it's now disposable, right? The singing cards that we get or receive have actually a fairly sophisticated integrated circuit in it, and it's a use once computer, so it comes out, sings you a song, and then you throw it away. Now, why does everything have a computer in it? Well, we basically know because of scaling, Moore's law has made the gates that we use to build computers incredibly cheap. So they exponentially decrease with time. And then because of Dennard scaling, that is, as we scale technology, not only do they get cheaper, that is, we get more gates, every gate takes 1 over the size. So if I make everything half as big, I get 4 times as many gates. It turns out by making the transistors smaller, they actually went faster. So they would run at twice the frequency. But the most important thing is that the energy that it cost to do a gate evaluation, which was CV squared, fell by a factor of 8. Okay? So for every scaling of 2 in technology, what it meant is I can do 8 times as many gate evaluations per second at the same power, at the same area, so roughly for the same cost. Okay? So for 30 years or so, we've been seeing this kind of exponential scaling in the underlying technology, and that's led to an expectation on our part that we can carry in our pockets, right, computing capability that far exceeds, the supercomputers of yesteryear. And in my formative years, right, I graduated from college in '78 and started my graduate program. The fastest computer around was the Cray 1. It's humbling to think that the Cray 1 now fits on a piece of silicon, and 45 nanometer technology is under 3 millimeters squared, and today's technology is probably under 1 millimeter squared. It would run not at 80 megahertz, which seems pretty slow these days, but probably run at close to 1 gigahertz, and wouldn't dissipate 115 kilowatts, but rather would dissipate under a watt. So this scaling of underlying technology has really enabled us to just imagine that, the things we carry in our pocket are incredibly powerful, and pretty soon that we'll wear them on our wrists instead of carrying them in our pocket, or the things we carry in our pocket will be even more powerful. Okay, we could also look at the performance of microprocessors. So I've just plotted some data that my students and I have been collecting for a while. So it's an interesting website is cpudb.stanford.edu. It just has data on microprocessors from the 4004 all the way up. So if you just want to download that data and play with it yourself, you can look at it. There's lots of statistics on the processors. But what you can see is this improvement in processor performance since this started with CMOS processors in the mid-80s. If somebody could turn down the volume in the room so it doesn't echo, that would be good. But yeah, no, it's. Oh, is it over here? Just turn the room volume down. Yeah. Okay. I think, yeah, that's much better. It's less amplification here, but I'll talk louder. I prefer it that way. So this all looks good. Now, if you look at it carefully, you can imagine that this looks like it's bending over at the top end. Oh, I got my pointer not on the right screen. Over here, you can imagine it's bending over a little bit in the top end. But it's the problems we're facing are much more dramatic if you look at basically base computer frequency. What? If you look at the frequency that microprocessors run at, what you notice in 2005, we basically hit this wall where the frequency that we're using for the processors no longer was increasing anymore. And it had been increasing quite rapidly up into that period of time. And in fact, if you go back on that performance plot that I showed you before, the whole reason for the performance improvements over the last decade has been small amounts of technology improvements and improvements in the memory system of the processors. Okay, well, what happened? Why did the frequency stop scaling is pretty well shown in the next plot, which shows that in the period of time, and again, so all this data is from CPUDB, in the period of time that the frequency was increasing rapidly, you'll see that the power density, this is in watts per square millimeter, was increasing rapidly as well. And finally, we got to the point where we really couldn't increase the power density that much anymore because the chips were getting too hot to cool cost effectively in a room that you wanted to be in, right? So in a server room, you could get higher power densities, but the fans got very noisy. Now, if you look, it's 300 milliwatts to a watt, and you think that's not very much power. But remember, this is power density. This is in watts per square millimeter. Your typical die is 100 to 200 square millimeters. So 1 watt per square millimeter is 200 plus watts of a chip, and that's what you couldn't basically cool anymore. So what happened was we had been increasing performance, but when we were increasing performance, we were actually increasing power. Well, wait, didn't Bob Denard say we shouldn't increase power through scaling? Well, if you look, we were a little greedy. So if you actually took the technology and said what the technology speed should be, you get a line which is kind of this purple line. But what happened is in the early 90s, there were a bunch of crazy people at Digital Equipment Corporation primarily that built a very short tick machine and demonstrated you could really improve performance by doing that. And then essentially the mainstream processors did that. Over here, DEC got out of business, so they don't have the machines up here. But pretty soon, everybody was on the short tick thing, so that by 2005, by the time we came to the end of this, we were about 10x higher frequency than we would have been if we just scaled with base technology. So if you think about it, the energy per operation, if it was scaling down, we were doing 10 times as many operations per second, so the power should have been about 10 times too big. If you go back, the energy actually increased by a factor of 30. I'll tell you where that extra factor 3, a little bit more than 3, came in. So you might think that we did this because we were greedy, but I think of it, we weren't really greedy, we were clever, because we were doing this arbitrage and paying things that people didn't care about, right? We're buying power, people didn't care about power, and we were delivering performance which they'd pay us money for. So it was a good arbitrage until it got to the point that we couldn't do it anymore. Okay, so we're now at a point in the mid-2000s, where basically the processors in your laptops, in your desktops, in the server rooms are all basically power limited, right? So for a laptop, the power limit's about 20 watts. For a desktop machine, it's about 70 to 100 watts. In a server, it's a little over 100 watts. And all of them, for various reasons, can't go higher in power density. So at this point, we're kind of stuck because now we need to do something to basically improve performance. Now, you might look at this point and say, okay, well, we've been stuck for a decade, but things will be okay in the future because we finally regressed to the norm, right? We continue to scale technology and things are going to be okay again. Okay, the problem is that's not so. And the reason this power problem is not going to go away is you can also look at how we scaled power supply voltage, which was the other important part of Dennard scaling. And what you realize is that during this period of time, we haven't been scaling power supply voltage according to the feature size like we should have. We've been scaling it only slightly faster than square root of the feature size. Okay? And what that means is that as we've been scaling technology, we've lost another factor of 5-ish because we haven't scaled voltages as fast as we should have. But what's even more troubling is if you notice in the modern technology, sub 90 nanometers, is we're not really scaling power supply voltages at all. Okay? And the reasons for that have to do with semiconductor physics and Fermi-Dirac statistics and energy barriers. I'll get a little bit into that a little bit later. But basically, we're not able to scale power supply voltages. Now, I should note that the data in this plot isn't exactly true. And the reason is that in order to limit power dissipation or reduce power dissipation, every microprocessor operates at a different power supply voltage. It operates at the power supply voltage that that chip happens to need to operate at to meet the frequency. And so what it says on the spec sheet is kind of the worst case number, but it's not the actual number. Okay, so you might say, okay, well, these haven't been going down because it's just the worst case. The actuals have been going down. But there are programs that you can download and run on your PC that tell you what the power supply voltage that your PC is actually running at. And so I've been doing that for various laptops that I have. And it turns out that the power supply voltages have been stuck pretty much at 0.9 something volts for the last couple generations. As Intel went to the FinFETs technology, so that laptop that I have and the laptop I had before that actually have the FinFET technology, then the power supply voltages have dropped by about 100 millivolts, so it's 800 and some odd millivolts. But I don't expect that power supply voltage to decrease very much in the future. Okay, and here is the computing's energy dilemma. We can define power as basically the energy it takes to do an operation. The operation could be an instruction or whatever you want to think about, times the number of operations you take a second, because power is just energy per second, right? So if I do energy per op and ops per second, that's energy per second, that's power. Okay, if I want ops per second to go up, because ops per second is what we call performance, if performance is going to go up and I'm power limited, energy per op has to go down. Okay? So the only way I can do more ops per second is if the energy op goes down. If the energy per op doesn't go down, I might have a technology that could allow me to do more ops per second, but I won't be able to do it because I'll run into one of these power limitations I talked about before. Everybody with me? Okay, so what are we going to do? Well, look, if you're a computer science person, you just don't worry about it. This is just some underlying technology. After all, the first computing machines were mechanical. Okay. Now that's actually a picture of Babbage difference engine 2, which happens to exist in the Computer History Museum. that's not very far from where I live. And if you ever get up into the Bay Area, you should definitely check it out. It is the most amazing mechanical contraption I've ever seen. And it operates, and periodically they do operate it, at least they used to. Okay, but we did that for a short period of time. Then we built tube machines, and they had their own problems. Then we went to, the transistor was invented, and the thing that really blew me away when I did some research is the first transistorized computer was built like 2 years after a transistor was invented. Right? So people were desperate for building computers out of something other than tubes. And then we went from that to integrated circuits, bipolar integrated circuits initially, then NMOS integrated circuits, to CMOS integrated circuits when NMOS integrated circuits got to dissipate too much power. So if CMOS is running out of steam, I'm not worried. There'll be some technology X. And if you read the ACM news, every 2 weeks there's a new technology that's going to rescue computing. Unfortunately, I don't believe any of it. And the reason I don't believe any of it has to do with these two problems. One is fundamental physics, and the other one is economics. So the reason we have problems with energy today has to do with leakage currents in transistors. We can't decrease threshold voltages, because if we decrease threshold voltages, we get too much leakage. And if we don't decrease threshold voltages, we have to keep power supply voltages up at a particular level. Okay, what this leakage thing is that the way all semiconductor devices that we have used work is there's some energy barrier, and that modulates flow of carriers. And carriers have Fermi-Dirac statistics, which means they're exponentially distributed. And so the amount of carriers that can go over a barrier has to do with KT on Q. You get exponential minus KT on Q times the energy barrier. Anyhow, if we're going to get rid of this problem and we're going to go down in voltage, which we need to do, we need to have a device that doesn't use energy barriers to modulate current. Okay? There are some things that do that, but they're different than every device we've used historically. Okay? Okay, the other problem is an economic problem, which is today you can buy an integrated circuit that has 1 billion devices in it, right? Okay, those devices operate at 10 picoseconds of delay, and each device dissipates, femtojoules of energy. Okay. In order to manufacture something that can build 1 billion things, a fabrication facility that can build something that has 1 billion devices at these characteristics, it costs billions of dollars. Okay? Those are just facts. Okay, I think these facts lead to the perfect catch-22. This is a highly scientific graph, which means on PowerPoint I drew a curve, that plots investment risk versus amount of capital you need. Now, I don't know how it is in the LA area, but in Silicon Valley, you can get money for the most absurd things, as long as you don't need very much money. There's way too many people who have made too much money by having a crazy idea, and so they think other crazy ideas should be funded. So if the capital that you need is modest, hundreds of thousands of dollars, maybe even $1 million, there's probably a person or a group of people who will give it to you. Okay. On the other hand, if you need hundreds of millions of dollars to $1 billion or tens of billions of dollars, there aren't very many people in the world with that kind of change. And typically, they want their money back. Okay? That's just, I don't know why, but they want their money back. Okay, so now let's think about what we need to do in order to replace CMOS technology. I said fundamentally the devices have to be very different. If you're building something that's very different, it's intrinsically high risk. Right? Okay, so it's got to be high risk. And of course, in order for me to be interested in using it, I have to be able to build a computer out of it or build something of sufficient complexity, because if it doesn't have, billions of storage locations and lots of gates, it's not going to be very effective. So I end up with this point in space that is very far away from the feasible funding curve. So I am not saying that there isn't a better technology than CMOS. There may well be a better technology for CMOS. What I am saying is I don't see any way to get from here to there. So those people who think that there's a new technology that's going to come out and rescue the world, I hope they're right, but I'm not going to bet my future on it. And I would advise you not to bet yours on it either. Okay? Now, you might say, I'm just a conservative fuddy-duddy and I don't know anything about innovation because after all, Google came from no place, eBay, Facebook, ARM is a dominant processor right now. When it came out, it was nothing, and then there's Nest and Amazon. The world has changed dramatically over the past 10 years. And how could you say that CMOS is not going to get replaced? Nothing's static. And I would say, maybe I am a fuddy-duddy. I've been called a fuddy-duddy before. But I have grown up in Silicon Valley, and I think I know something about the way innovation works. I could be wrong. But each of these companies got started by doing something very different than what existed. Google did not start out to challenge Microsoft for, desktop applications, which is what it's doing right now. It started out by serving a search in a very different way and a very different quality than anybody else. And when it did that, it gained control of the new web that was coming out, which Microsoft didn't even think was important enough to invest in at the time because it was just the web, it wasn't the desktop. And ultimately, the web ended up challenging the desktop far in the future, right? And you can look, ARM is challenging Intel, but when ARM basically started, it didn't try to challenge Intel. It was into these things that nobody cared about called cell phones, because who wanted a cell phone anyhow? And it turned out that Nokia needed a processor. They were looking for a stupid, cheap processor, didn't want to talk to Intel because they charged too much money, put an ARM in it, and as a result, now ARM and cell phones rule the world. So in each of these cases, you created something very different, and then that thing ended up growing and becoming a very powerful force. So if something is going to challenge CMOS, it better have a market segment other than computing initially, because otherwise it's not going to make enough money to survive and grow into something that can challenge CMOS. Okay. So what does that mean? I think that means we're going to have a future in which computing is done on silicon devices. Or it's going to be CMOS-like. Now, don't argue with me. They may put gallium arsenide, phosphide. I don't care. They're already putting germanium into my silicon. Who cares what the channels are made of? I don't really care. They're going to be made of transistors that transist, right? But if that's true, then the voltages are not going to scale very much, and we have essentially two realities we need to deal with. The first reality is the one on the bottom that I mentioned before. We are going to be power limited for now to the foreseeable future. If we want to increase the performance, the ops per second of the systems that we use and build, we are going to have to decrease the energy per op. That's one of the facts. The other fact that I think we should not forget about is the fact that today, silicon is absurdly cheap. Computing is absurdly cheap. I can buy a Bluetooth module that has a reasonable ARM core on it for, I think it's $1.50 commercial, which means that I can put communication and computing into nearly anything for no cost. So if I look at what's going to happen in the future, we're going to see tremendous innovative uses of computing, and it's going to go into lots of things. And that's why there's so many people talking about the Internet of Things. It is not that the Internet of Things by itself or anything is really new or different. We've been doing stuff like that. It's more a recognition that the cost of interconnecting things and putting computers in things is so cheap, people are going to do it. And the killer markets are going to be people who have some idea of that. When they did that, it actually provides something of value, right? Does that make sense? Okay, so I'm going to talk in the rest of the talk about both those issues. I'm going to end with the first one, but let me talk now a little bit about the energy limited issues. Okay, given this focus on energy and energy efficiency, I think what's really important to have in mind when you're trying to optimize something is what's the right metric space, what's the right way to think about things. So what I will tell you is I think the way you should think about anything you're building if you're worried about energy is in an XY axis where the x-axis is basically your performance and your y-axis is the amount of energy it takes to do that operation, right? So I can get higher performance and lower performance, and I can get different energies. So everything I build, every design I do, every computer is a point in this XY space that has some performance and some energy per op. And when you do that for no matter what kinds of things you're designing, you always find out that there's this case of diminishing returns. Right? So as I try to lower the energy, at some point I can lose as much performance as I want, but I'm not going to change the energy very much. And similarly, as I try to improve performance, I can add as much energy as I want, but I'm not going to be able to improve performance past a particular point. So there's this law of diminishing returns that always happens. Now if you look at this, this is exactly bad if we're power limited. Because it says is that if I try to increase the performance, the energy per op goes up, and the only way I can increase performance is if the energy op goes down. Right? This is bad. Okay. That is the reason that everything you buy today has multiple processors in it. Okay. Why does your cell phone have multiple processors? Why does your laptop have multiple processors? Didn't before? The reason is pretty simple. It's because of this curve. So if I now put 4 processors in this, let's say I wanted a high performance point. So I wanted a point up around here someplace. If I put 4 processors in the unit, what's going to happen is I'm going to be able to slide this curve over by a factor of 4, because if all of them are working on it, I get 4 times the performance. But now for this performance point, it means instead of being way up here on the curve, I'm actually down over here on the curve, right? Because each processor is only delivering 1/4 of the peak performance it was before. And so I can get more performance by having each processor run slower than it did previously if I had a single processor. Okay, or less performance per processor, more performance total. Does that make sense? Okay, and that's exactly what happens, and that's the reason that your processors now have turbo boost. And, if you have an Intel machine, it has turbo boost. You know what turbo boost is? Okay, it's Intel running the processor at the power point that it could to get maximum performance, which it can't do if it has multiple processors on because it will exceed the power budget. So what it does is it ramps down the power supply normally, so it can run all the processors, because if you're running all the processors, you get more performance. But if you don't, then I'm going to move up that power curve. I'm going to make it less efficient, but I'm doing less hops per second, so it's OK. Does that make sense? OK. Now, this is what I hate about the popular press. They did this with leakage. Leakage was increasing, and they said, oh my God, leakage is going to increase dynamic power. This is like total BS. Never did, never will. So they look at this and they say, oh, we now have 4 processors on the chip. Well, we're going to have 16 processors and 32 processors and all the rest on our chips, right? We're not going to do that. And the reason we're not going to do that is for the same reason. Okay? Like, we did the first thing. Now when we move, once we've already moved off the steep part of the curve and we're on the less steep part of the curve, if I make more parallel processors for the same performance, I can only move a relatively small amount in energy per op. Well, that means I only get a relatively small amount of performance out for the same power budget. Right? And whether it's 4 processors or 8 processors, 8 processors or 16 processors, I don't know. In the current cell phone processors, right, there are things that are being shipped with 8 processors, but they never use 8 processors. There are 4 low energy processors and 4 high energy processors. So they're just doing it from an energy efficient perspective. They're not doing it to get 8 processors actually running simultaneously. Because they can't, because it dissipates too much energy. So I think we will see tens of processors on a die, but we're not going to see much more of that, except if you go to GPUs where they call a lane a processor, and don't believe them. Those are vector units. Those are different. Okay, but this whole thing about being able to do parallelization kind of makes weird, because now what is the trade-off? Because the trade-off seems to change depending upon how many things you put in parallel. What should I do there? So if you have an application that is parallelizable, that is, you can run it in parallel, I think the metric space changes, because then what you're interested in is you're still interested in energy per op on one axis. Okay, so if you're talking about floating point, it's watts per flop. Okay? But on the other axis, what you're really asking for is not what the performance is, because if it's parallelizable, I can make the performance anything I want. I just put more units down, right? So what I'm interested in is how much silicon area does it take me to get a certain level of performance. So it'd be square millimeters per gigaflop. Okay? And what you see, again, is you have this law of diminishing returns, that at some point, at the minimum energy point, it doesn't matter how much silicon area you provide, it's not going to get you much lower amount of energy per op. And similarly, if I try to add more and more energy, there's a point where I can't just go faster in a particular number of square millimeters. Does this make sense? Okay. And it's this reason that I am not optimistic about all the sub-threshold. There's also a bunch of people talking about sub-threshold or near-threshold computing. If you look at near-threshold computing, you are at the very flat part of that curve, and you are spending a lot of square millimeters of silicon for almost no energy savings. Maybe you're going to do that, but I don't think so. I think it's more economically viable to cut back the square millimeters and spend a little bit more energy in the ops. So that's another thing that I think that there's a more discussion of than it will ever really happen, just because of the marginal return laws. Okay, so if we think about energy optimization and these sort of where you are on the plane, it all makes good sense. Now the question is, we've been doing this for a decade, because remember, we hit this problem in 2005. We now have a very shiny ball. We have been polishing this ball for a long time, trying to get the energy efficiency up. We're doing really well, or Intel's doing really well at it. Okay, so now what are we going to do? Well, people produce these graphs that say, here's the energy efficiency in ops per milliwatt, in energy per op. And they say CPUs get really poor energy per op, that the DSPs and GPUs are better, but what's really the best is custom silicon. You build ASICs, everybody knows ASICs gets really good energy, really low energy per op, lots of ops per milliwatt. And this is a plot that was put together by Dan Markovic, who's here actually. Okay, this notion of specialized computing has been very big in the computer architecture space, so there's lots of work about dark silicon and building specialized processors for different application spaces. We've got a whole center here on doing application-specific computing that tries to leverage this to increase energy efficiency. Okay. And look, I was in this camp. I was one of the proponents. I was doing specialized hardware. I built a hardware generator and all this other stuff. And then there are a couple things that caused my research group to sort of pause and take a look at things. So there's one thing we should check before we talk about specialization. And that is the memory system. So this is a plot that I showed you before that showed the trade-off sort of in energy efficiency by performance. This plot is actually a plot of the energy efficiency of microprocessors over time, historically, normalized to put them all in, I think, a 45 nanometer technology, or maybe it's 32 nanometer technology. Okay, so I tried to normalize them all. And what really bugged me about this curve was the most energy efficient processors were done in the 90s. that just seemed wrong. I mean, we've learned a lot of things about building energy efficient processors over the past 20 years, and it seemed wrong that the most energy efficient processors were built in the 90s. At first I thought this was great because they're the simplest processors, and I thought, oh, great, simple processors are more energy efficient. But then, the Atom came out, that's a pretty simple processor, and it wasn't as energy efficient as the old ones were. And then I realized that we had made a terrible mistake, that we had forgotten to scale the cache system for the processor, and we improved the frequency by a factor of 100 or 1,000, but we didn't change the cache structure, so those processors would have been waiting on memory all the time. And so we added a reasonable cache hierarchy to them, and when we did that, the old points are grayed out, the new points are in color. You'll notice that they changed by factors of 3 or 4. What that said was the cache system dissipated 3 times as much energy as these simple processors did. I thought, ooh, that can't be possibly right? But we double-checked the numbers, and it seemed that we hadn't made a mistake. So I talked to a friend of mine who was building an 8-core out-of-order issue machine, a standard high-performance machine. And when we had them break down their logic, this is what we got. Basically, the 8 cores took less than 50% of the total power. The L1 caches took about a little over 1/6 of the power. The L2 caches were 1/6, and the L3 caches were about another 1/6. Okay, now, if we look at a single processor, that single processor is way less energy than the memory system. Now, of course, the L1 caches would probably divide by 6, so that's not such a big thing. The L2 caches only divide by 3, so it's still sizable, and the L3 cache doesn't change at all. So you still get less than 50% of the energy of a die would be dissipated by a single core. So said differently, in order to amortize the energy of the memory system, we have to have more cores there, because otherwise it's all in the memory system. Okay, that's on the processor die, but of course, you actually have DRAM outside the processor die, and the DRAM dissipates energy too. Okay, it's maybe half, a third of the die energy, but still, that's a sizable fraction. So, how in the world are accelerators going to help? Isn't there a guy called Amdahl or something, and he said something about, residuals and how much things, and if 2/3 of the energy are in the memory, how is the third going to give you factors of 1,000? Right? So are these guys lying? Can't be. He's a UCLA professor. He can't be lying.
But he was at Stanford.
Yeah, right, that's right. He was at Stanford. Maybe we corrupted him. No. Okay, so here's ASIC's dirty little secret. Every application that has been mapped to an ASIC has absurd locality. It doesn't have good locality. It has absurd locality, which means that you feed the data in, and you do this enormous amount of computation, and you get a small amount of data out. And so the amount of memory that you actually touch is very small. And it's not just the DRAM that you're touching is small. Actually, you don't do very many cache accesses either. It's a lot of local stuff. And if you look at kind of the breakdown of how much things cost, cache accesses probably cost tens of picojoules. DRAM access costs even more. It's a nanojoule for 64 bits, right? If you think about floating point operations, there are only a few picojoules. Integer operations are much less. So that, if you're doing memory accesses, your 70 picojoule instruction isn't that big an overhead. Okay, it's a factor of 3 or 4. But if you're not doing memory accesses, the overhead's factors of hundreds. So you can understand that if you had an application that didn't need to access memory, you could get tremendous efficiency gains by basically building custom hardware for it. Okay, so I think the truth is, To get energy efficient computing, it's more about the algorithm than the hardware. If your algorithm does a lot of memory fetches, you're not going to be able to make it very efficient. So if you think about it, you can have the space of all algorithms. Within that space, I say the GPU algorithms, these are data parallel algorithms. And within the space of data parallel algorithms, there's a spot of data parallel algorithms that have absurd locality. And what we're really trying to do is move our application to that small spot, because that's what will give us the most compute efficiency. Does that make sense? OK. So is this good news or bad news? If I wanted to save the world, it's probably bad news, because I don't think I'll be able to save the world. Right? There are algorithms that won't have absurd locality, and I don't think there's very much that we can do to make them more energy efficient. And I mean this in a global sense. It's not that we can't do factors of 2 or 3. I think most software, by basically optimizing the software, we probably can get an order of magnitude out of the software. So, right. But from fundamental levels, I don't think we can do very much. But on the other hand, if you're a computer architect, having a very limited domain that you have to serve, that's good news. It means I don't need to worry about the fact that I can't do X, Y, and Z and have people complain, because I can say, look, you can't do X, Y, and Z, because if you did, it would take too much energy. OK. So what are the class of algorithms that have this really absurd locality? They tend to be stencil kinds of operations operating on a block of data. And the reason they have such high locality is you typically read from a block. OK. You do some operations on that input stencil, and then you do some reduction of the stuff that you computed, and you generate a single output. But the important thing is that when you operate on the next piece of data, you basically reuse much of the data you had. And in fact, you typically only fetch one new object, which is the green thing. The red things on the leading edge you've actually seen before in the previous passes, so you have a line buffer or something to store those. So you keep the local set within your registers. You're only fetching the leading edge. And of the leading edge, only one thing on the leading edge is actually coming new. Moreover, because these computations are so efficient, I can't actually write the data out back to DRAM, because that DRAM write would be way more expensive than the computation I did, even if I did 25 ops or something like that. So typically, if you look at how these machines are actually built, there is a buffer that buffers the data that then feeds it into another stencil, which then feeds it into another stencil. So you literally build this hardware pipeline, so the data feeds in at one side and comes out of the other. And in the intervening period, you have ops and only small local memories and no global memory, no L2 or DRAM. So we've been working on a system to explore the space. We've developed a high-level language, which is a graph of the stencil kernels. It's a domain-specific language called Darkroom, and it's available on the web if people are interested in playing with it. We can map Darkroom right now to either x86 assembler or to basically Verilog. And that Verilog can be mapped into FPGAs or ASICs. And currently, we're trying to build a computational camera platform that we hope to have in the beginning of the year, that a person can write their own image processing application, download it onto an FPGA, and then basically take that on a mobile platform and use it as a camera. OK, so if I believe that for energy efficient computing, we're really going to need to change the algorithms that we use, that means we're going to need to enable the application experts to play, because they're the only people who know how to cheat to change the algorithm and still get the right result. And that gives rise to this trade-off that we said before, which says that if we make it too hard for them to play, they are not going to play. Right? If we make it so they have to learn Verilog or do other things, there's no way that they're going to try out and understand what the limitations are. We need to give them an an environment, a software environment, a language that they can play with, that they can write their algorithms, they can try it out and understand what works and what doesn't work and make it pretty easy. And then when they get something that works, to allow them to basically execute on that and get some benefit to incentivize them. And so we're working, again, to try to build that kind of prototyping platform. And that's something that we hope we'll have in the near term. I'm going to skip this because I'm running a little long on time. So let me get back to that big statement I said about our CMOS future. I said, for things that are power limited or performance, dominated, we're going to be power limited and we need to increase the energy efficiency. But there's a whole other class of things that basically are going to be enabled by extremely cheap computing and communication. This is a Nest smoke alarm, I guess, which doesn't have bleeding edge technology in it, and yet was a very successful product. Okay, so I think one of the things that we need to really be able to enable is how do you get people who have ideas for this to be able to create things like this, right? And again, if you require the people to have hardware design experience to be able to create applications like this, you've just decreased the number of people who can basically play in this space by orders of magnitude, right? So how do you get somebody who can basically write apps to be able to create hardware? And what I'd really like to do is to create an app store for hardware. In my view, one of the biggest innovations that Apple did in the iPhone initially was the creation of an app store. Because what they realized is that by creating an ecosystem, they could enable a group of people outside of themselves that they don't pay to create products that make their products sticky. Okay? And so what they did is they did a bunch of work. They created the development framework for the iPhone, which has a steep learning curve, but is very powerful. So you don't need to understand a lot of the stuff about how the graphics on the phone works. You just need to understand the calls. And that allowed people to build apps. And then when it became popular, there was even more middleware now available to make it even easier to build iPhone apps. Okay? So what that did is it enabled a huge community of people to come in and play. Most of the stuff they built was crap. But some of it was really good. They got rich and famous, and that encouraged more people to build stuff. And so that the amount of things that you can buy on that store is actually pretty impressive these days. So the question is, could we do a similar kind of thing for hardware? In order to do that, we need to have a set of tools that enable people without too much hardware background to basically play and provide a way to monetize those results for things that are successful. Okay? I think the Internet of Things, that whole environment of trying to make things better, is a perfect place to create such a thing. I don't know exactly how it's going to happen or who's going to win, but I think something like this is going to happen, and there's no reason that we couldn't enable people to build hardware. Because look, let's face it, the hardest thing about building hardware with embedded controllers and all the rest is knowing what embedded controller to use, understanding a lot about that system stuff, and that truthfully hasn't changed very much in a decade or more. So we should be able to regularize it. So I think the challenge here is a challenge that is best exemplified by the Arduino. I don't know if people here know about Arduinos, but Arduinos are they're a really stupid microprocessor, and they can almost do nothing. But the point is they're very easy to use. And they attracted two sets of users, which I think is the requirement for having a successful platform. They attracted people who just want to build stuff and don't know very much, and they enabled them to do that. So that's important. But if all the people that you attract, if the only people you attract are those people, you'll get a site that gets stale very soon. Because the new stuff requires experts to basically incorporate it in. So you also have to encourage experts, people who know something about the hardware, to come in and basically extend the site and have the new routines that the users can use. And so I think the trick in creating this kind of marketplace is how do you make the marketplace interesting and easy enough to use so the novices come in, yet useful enough for some of the people who know better to still use it and put their knowledge into that. And I think that's kind of the trade-off, and that's the tricky part, but I think it's doable. So in the end, I really do think that computing and the change in computing is slowing down. But I actually, that doesn't make me pessimistic. I'm pretty optimistic about the use of computing and what we're going to be able to do in the next couple decades. Because even though technology scaling is slowing, and I believe it will eventually stop, the capabilities of the technology even today are amazing. And our utilization of that is not anywhere near at the level it could be. So if the future is going to be very application driven, okay, we're going to need to enable people who actually know what problems need to be solved. And sometimes they're not the nerdy engineers, sometimes they're more arty kind of people. But we need to enable them to leverage the technology. And perhaps, since technology is scaling more slowly, we can leverage that fact by building more powerful tools that will enable a new class of designers. And we'll have a renaissance in basically the creation of interesting computing systems, like what happened in the early 80s when basically ASICs first were developed. And there's a sort of a boom in people using silicon technology. Thank you all for your attention. Yeah.
Okay, man. If you make this go very fast and we can create lots of interesting products, what happens with the support and stability of ecosystem? Things come, then disappear, I invested in it, nobody's there to help me. What happens?
Well, I think that
Should it be developed together? In other words, we need some other infrastructure that follows this?
well, so what you're saying is when you develop a product, a lot of the cost of that is basically doing product support, right?
Yeah.
So the question is how much customized product support do you need for your product? How much of that can be basically part of the infrastructure, right? So, I mean, I don't actually know how Apple does product support, right, for all the individual products that they launch.
Not too much.
Yeah, so I don't know.
You buy another app when this one doesn't work.
Well, maybe that's what happens because it didn't cost you that much money, yeah.
Yeah, or you're going to get standardized interfaces that the community settles on, coupled with modules. I mean, we don't need the support for the nuts and bolts that we buy the hardware for.
Right.
And many other interchangeable parts that need standards. So
Yeah, well, look, so standardization is a very tricky thing because standardization is often done not by standards bodies but by individual corporations. So Apple has standardized what the interface is. Google has standardized what the Android interface is, and they update it and change it because they can, and people basically deal with those updates and they have to worry about compatibility. So I definitely think if we look forward, there will be some developing standardization for whatever markets happen because otherwise you can't build an ecosystem. That's the reason the standards develop. Right. Now, whether it's developed explicitly by a committee or by a very successful product that people want to gang onto, I don't know.
But can you say something about where you see, say, the Arduino ecosystem going?
So the Arduino ecosystem is basically, I mean, what you can see now is it's migrating up. It basically started on Atmel processors. But now that ARM processors are so cheap, there's Arduino that's been ported to the ARM processors. But the Arduino system by itself is really built for very simple things. And I don't think it is scalable up to where you want to be. It doesn't have any system surfaces. You're basically working on bare metal. So my guess is that we will see a different system, and there might be a different operating system. I don't think it's going to be Linux on the small embedded things either. Phil Levis, a faculty member at Stanford, is interested in basically building a new kind of OS, system services layer. He built TinyOS initially when he was a graduate student at Berkeley. So I think there is an interesting question about what the level of system services you want on your embedded device. I think that's going to take some time to shake out, but I have no doubt that it will shake out. Yeah.
So imagining you, before you were born, giving this talk in 1946 and talking about the fundamental limits of vacuum tube computing and power and reliability and everything else, and saying, look, there's just no way we're going to see much change in this. And what Shockley, Bardeen, and Brattain did, Bell Labs didn't require an enormous amount of capital. And he said, within 2 years of that, we had computers. So the question is, how is it different now than it was then? Why does your sort of gloom and doom at the beginning of your talk apply now, but it wouldn't have applied?
So it wouldn't apply back there because the capitalization to basically build something was very small. So if you think about it, the people who built the early transistor computers bought the transistors, and the only capitalization that was needed was to manufacture the transistors, right? They built all the boards and everything else by hand. Does that make sense?
I guess I don't quite understand. So obviously manufacturing and everything else took a lot of money, but doing the research didn't require a lot of money, right?
No, what I'm saying is that, no, it didn't take, what I'm saying is once they figured out how to build transistors, people started building transistors. They were really crappy transistors. They built them all different ways. But that didn't take a huge amount of dollars. That's why there were a whole bunch of companies that started building transistors. Once those transistors were built, lots of people took those transistors and put them into different things. The capitalization to do that was not large. It didn't take $2 billion to build a manufacturing facility to build something that would be competitive. Right. So, and I would say also that there was no in vacuum tubes, people were searching for a solid state switch. It wasn't, it wasn't an accident that they did this. In fact, people had predicted MOS switches before the bipolar switch. The problem with surface states made that not work. So there were lots of things, or let me say it a different way. In the technology space right now, in order to get into volume manufacturing, the technology has to exist for about a decade in order to figure it out how to stick it in the manufacturing process. Okay? Because things have to be developed to that level. Okay? So if you don't see something now that you admit that you think can work, you're a decade away from it happening. Okay? I don't see anything now, and I don't see any research ideas now. I can think, yes, there's lots of people doing research. I hope they're right, but everything that I think about is not going to fundamentally change this. Tunnel FETs. Anybody here doing tunnel? No, it's not the E audience. Tunnel FETs are interesting, but they actually modulate current by using density states, and density states doesn't have the big range that, I don't see anything that actually is going to solve this problem. Now, I hope I'm wrong, but the other thing is if you try to do it for computing, I think you'll get smushed by the installed tens of billions of dollars in the computing, in the silicon infrastructure. Just my opinion, yeah.
So I'm excited but also intrigued by this idea of a hardware app store. Because even when you look at software ecosystem, there are a lot of problems with the testing and debugging and evolution. And how do testing and debugging and evolution work out for hardware app stores?
Yeah. So that's the reason I really like that. That's the part that I'm most interested in. Because if you've ever built hardware and software, I'm teaching a new class. It's a beginning EE class. And the students build a couple transistors and connect it to an Arduino and build different things. Debugging that system for the students is incredibly hard because it doesn't work. Well, did they put the wires in the wrong places? Does their code have bugs in it? Right? How do you do that? And I actually think that when I build pieces of hardware, the first thing that I always do is I assume everything's broken. Maybe it's just, I see designers basically assume everything's broken, or assume that when your chip comes back, nothing will work. It's not that the chip's broken, but you're probably using it wrong or something, but nothing will work. So you carefully build a procedure that allows you to kind of check out various different paths, and you incrementally go up, and you get assurance in this, and then you check some other stuff. So if you think about it, this is the same problem with software, right? You use libraries from lots of people. Those libraries should work, but maybe they don't work. And when your program doesn't work, you have no way of it's very hard once you're using all these different modules to know where the error is. So what that says is if we're going to build a system that has automation, we better also automate the testing and put as kind of assertions in the interfaces of the things that we're using, so when things break, we can have some indication of, this didn't obey the spec that you said it was going to obey or something like that. So I think that's an extremely interesting research question, which is the reason I like this, because that's what I hope to do some research on. Okay. Oh, yes. Yeah, please, sorry.
So the hardware design is compiled from a high-level language compared with manually tuned hardware design. How much will be the difference of their performance? If there's a big gap, do you think it's a challenge?
Yeah, well, so I'll say two things to that. The first thing that I'll say is that I believe that if you provide the right abstraction, right, so if I do a narrow domain language and compiling it from the domain language, I can do very well. Because essentially I know already kind of what the proto-architecture is, and I'm forcing people to write into things that I know I could create an efficient hardware on, okay? So I actually think that will be okay. But I'll say another thing, which is that I'm old enough to have been an IC designer in the early 80s. This was when placement and route, I don't know where you were during the early 80s, but where placement, route, and synthesis and everything was invented. And I remember hearing about the synthesis people and the place and route, and I thought these people were totally idiots, total idiots, because they weren't paying attention to wires, and I knew that wires were really the most important thing, and all this other stuff, and that all this other things that all the IC design guy said. And the truth was, the early synthesis tools were crappy, and the early place and route systems were crappy, but it didn't matter. And it didn't matter because it enabled a whole new group of people to take advantage of the technology that couldn't have access to the technology before. And the truth is that the number of IC designers in the world at that point was very small, and there was no way that they could do all the stuff that people had ideas in their heads to do. And so the creation of the ASIC revolution was really an enablement of a whole bunch of people to get access to silicon that didn't have access to silicon before. And maybe their designs weren't as good as it could have been done if they were done by IC designers, but it didn't matter because they could do them, and they were way better than building them out of chips on boards. Okay? So let's roll forward 25 years to where we are now, or 30 years. We're in the same situation we were before. The problem is that we can, in our current place and route systems and everything else, build exquisite hardware. It just costs you $50 to $100 million to basically do it if you roll up the design costs and the firmware. It's mostly over half the cost of a chip today is basically in the embedded software. Okay? If we could figure out a way to decrease that cost to under $1 million, 100,000, remember whatever that number was that you could get any idiot to give you or some idiots to give you, then you can enable a lot more people to play. Okay? Those systems would not be as good as the systems you could do full custom, but it doesn't matter because they would satisfy that application. Okay, so I actually think there's a market space here for doing that. The question isn't how does it compare to the ASIC. It really says how well does this compare to what you could do on an FPGA or something else that's available. Okay, and I don't know, but I do think that one always has to be careful when you complain about how good this is against an existing things, because you have to compare the amount of capital that you're willing to spend. And the real question is, for X capital, what is the best answer you can get? So.
When you said designers are assuming things are broken, you were speaking about new chips. I mean, what environment were you speaking?
I'm a chip designer, so I always assume when I design a chip, I assume the chip's not going to come back. And when my chips design chips, the chip is going to come back not working or appear not to work. And therefore, there has to be a very good set of observability in the chip so that you can figure out what's really going on and you can realize where you made your mistake.
It's typically your mistake rather than the fabrication, some fabrication.
Yeah, well, the fabrication mistakes, those are easy to check. It turns out fabrication mistakes are easy to check because you have so the thing is, once you have the chip defined, you have a set of logical equations. It's very easy to get a set of ones and zeros that check whether the logical equations were implemented correctly. So that's easy to do.
So it's your algorithm based.
Right, but the algorithm, there's no formal specification of what it's supposed to do, so when it comes back, it's the same thing of a program, right? How do you know the program works? You don't.
I mean, I'm interested because it's all, for decades, it seemed to me that the biggest problem on the software side of the world generally is programmers tend to assume things are right. because they think they can fix it later. And we see that in the big software projects failing all the time.
Right. Well, chip designers can't actually fix it later because it's extremely expensive to get the silicon back. So we have a different method, a different.
That's why we like FPGAs.
Yeah, well.
You need the mentality of the civil engineers. The concrete board is real hard to undo.
Maybe in the interest of time, let's ask the two last questions, and I will ask the last one so that you only have one.
Okay. Any more questions? Yeah.
Seems like currently lots of power consumption now occur at the memory system. But currently there are some novel technology like non-volatile memory. What do you think of this kind of technology? Would they somehow be one of the solutions to encounter this powerful?
Okay. So my conclusion is that the only reason novel technologies are less energy than real existing technologies is because they're imaginary and they're not real yet. And we all know that things, as they become real, get less good. Okay? So if you think about where the power dissipation comes from in a memory, it's all about the wires that you draw in the memory. It's the length of the wires. It's all CV squared. So I see no reason why they should be lower energy. In fact, the energy required to write a non-volatile memory is strictly larger than to write an SRAM cell or a DRAM cell. So to the extent that they're smaller and the wires are shorter, there's a possibility, but it's really hard to imagine that they're going to be much smaller than a DRAM, because DRAMs are pretty small already. So I just don't see it, right? And nobody who's told me that they're better can tell me why they're better, right? So I just think it's because they're not real yet.
Is it possible that they are running the new technologies in the last part of the power versus speed that we showed?
Well, it's one of the things is that SRAM cells have problems with lowering voltages because of stability issues. And so one could imagine that you could run these other things at slightly lower voltages. On the flip side, SRAMs do sometimes low swing sensing, which already does lower swing for lots of the long wires. So when I look through the physics of how they work, I have not been able to see a reason why they should be lower energy. And when people who claim they're lower energy are not from the group of people that I would believe, right? They're architects that talk about this and talk about the great things. So I'm skeptical, right? I'm skeptical.
By the way, my question is somewhat related to this. Typically, we have three parts in a power chart. One is the computation, the other one is memory, and then have communication.
Right.
In your pie chart, you only have two parts, really, computation and memory. I assume you lump the communication into the...
Well, so if you look at a single, right, so on a processor, all the communication happens in the memory system, because all the crossbars, right, between the processors and the shared L3, or between the L3, which is segmented actually to the different memory controllers, that's all in the memory system. And to me, memory is just communication, right? You can communicate either physically in space or you can communicate in time. So like when you write a variable in and store it in memory, that's really communication. You're communicating it to another part of the program farther in the future. So it's all about locality, right? So yes, I lumped it in there. And I think one of the problems that you need to face when you try to build very efficient architectures is the wire energy and everything else starts mattering if you build very big computation blocks. So, okay, well, thanks.
Thank you very much.